my name is Daniel Hudson, and I'm presenting Lab 4 of Physics 2, where I work with some simple electric circuits to demonstrate currents and voltages. So my initial setup was a series circuit on the circuit animation platform. To do this, I used the two resistors as shown in the right here. One is 47 ohms, one is 100 ohms, and then I used two ammeters to measure the currents and the batteries to measure two 1.5 volt batteries. So as you can see, we have a total voltage in the system of 3 volts and current in the system of 0.02. The current is the same at both stops because the resistors are in series, which allows us to use the driving equation here, which is that current is equal to voltage over resistance for each capacitor. And because these resistors are in series, we can just add them together to get a 3 volts divided by 147 ohms, which gives us the current of 0.02 amperes along the length of the circuit. This fits in with the general node rule of physics, which means that the current coming into one going out of one resistor is equal to the current going into another. So I then messed with the series sum to measure the voltages. First, I took off the ammeter on one of the ammeters and measured the voltage across the gap in between where that ammeter used to be, and I got a voltage measurement of 3 volts, even though the other ammeter that was still part of the system read 0 amps. This is because this is due to the loop rule. The loop rule states that around a closed circuit loop, there is no overall voltage difference. But because I removed that ammeter and opened up the circuit, there is now a voltage difference present just between the two wires there, which was 3 volts equivalent to the battery. I then was able to graph it, as you can see in the bottom right graph, which is once I reconnected that empty spot with just a wire, I graphed the voltage here at a few different points. So as you can see here, we start off with an increase in 3 volts from the batteries, and then from B to C is just the wires. C to D is the first resistor, the 47 ohms, and then E to F is the second resistor. So these are the only two things that are causing a voltage drop, so they must combine to equal the initial 3 volts made by the battery. I also used a bit of a parallel series, which added an ammeter alongside the 100 ohm resistor, and this increased the overall current of the circuit to 0.06, sorry for the typo there, where we now had a new effective resistance that was somewhat smaller because there was another path for the electrons to flow. I created this circuit next, which is simply a light bulb, a capacitor, and a 9 volt battery. I used a 10 or a 0.1 capacitor rather than the 0.2 in the directions, so that will explain some of the somewhat different numbers I got compared to some other peers. But as you can see, the 20 ohm bulb took slightly longer to charge and to discharge the capacitor than the 10 ohm bulb. And we see this continued as I upped it to a 30 ohm bulb. I graphed the voltage difference compared to time. So as time went on and as the circuit continued, the capacitor charged up and took electrons, basically hoarded electrons from the rest of the circuit, causing the light bulb to dim out. And I graphed this change in voltage as the capacitor stored electrons versus time, linearized it using this equation, and got this graph. The time constant was about 3 seconds, which is where the voltage differential is. After about 3 seconds, the voltage differential is 1 over E. So that is, coming off the 9 volts that we started with at the beginning. So just some final questions as we try to translate this computer animation circuit to real life. This is an idealized version. In real life, the wires and the ammeters and the voltmeters, that sort of thing, would provide resistance and contribute to decreasing the current. So the the resistors wouldn't be doing as much work in that. And additionally, when we take that last circuit to real life, the capacitor isn't charged as quickly because of that resistance. And if we were to remove the bulb, the animation has the capacitor charging instantly, and that doesn't occur in real life, just due to the presence of other things in the environment, like resistance from the wires. Thank you for watching.